Welcome to this presentation. We'll be talking about tips and tricks for when you're doing modeling. I'll look at both using these in Solidworks, a little bit in Ansys, but the emphasis will mainly be Solidworks. You can do it and apply them to both. So let's get into it. If you need to access the notes, which actually I would encourage you to because there's some outline there, go to the tips and tricks file in the notes folder, and then from Solidworks download the part twist, which we'll be using in this lecture as well. All right, and just to look at that tips and tricks really quick, this is what it looks like. So you can see that stuff I'll be talking about here first for the time-saving tips, a little bit of outline, things to highlight, mesh verification, etc., etc. So you can come back to this notes really quickly as opposed to watching the video, or you can watch the video. I'll have it outlined as well below, and you can skip to the parts you're interested in. All right, so the first thing is the time-saving tips for modeling in SolidWorks. So let's go look at those. And if you click on the file, it actually comes first into the channel, or the playlist right here. This is a SolidWorks time-saving tips on the SolidWorks channel. It's a little bit old. It's with SolidWorks 10, but still I think very relevant, even though as I'm recording this, it's 2016. The one I like first is the view manipulation.
If you've been using SolidWorks,
and you can watch this. It's great for moving the thing around, but the big thing they highlight at the end is using the control button and mouse gestures. So let me show you what that looks like. So I already have the twist part open, and the mouse gestures is you just hold down your right button, right click, and start moving in one of the directions, and you'll see this pop up. And so we can, one of the most popular one is moving to isometric view. And so you can see which is the front plane, which is the top plane, and which is the right plane, always. And when you go to isometric view, they're always in those locations. But I also use right view a lot. I use top view. Right. So these are all valuable to use at some point or another. And then you can obviously just middle click and slide around to rotate as well. But mouse gestures is a nice quick way to get to view different things. The other one I like that I use sometimes is when I'm trying to click really focused areas, and I don't want to have to keep zooming in and zooming out and doing all this stuff, moving back and forth. And now I just messed up what I did there. Just hitting G. So move your cursor to where you want to see, and then click G. And what you get is the magnifying glass. And you can magnify even more if you want to. And you can hold down Control and middle click and pan to get right in the right spot, so you can click, right, or even hit the sides of it, and that moves it well. So I'm zoomed in pretty good, so it's really sensitive. But I can get right on that edge, right, if I want to get the edge I want. All right, and then it gives me that selection that I need. All right, so that's a nice option there too. But again, look at the other ones there. Maybe watch through all the videos. A nice tips and tricks as you're moving through and getting more comfortable with SolidWorks. All right, so that was kind of the first thing I wanted to highlight. The next thing I want to go back to is verifying your mesh. All right, what does this mean? What does it mean to verify your mesh? How do we know our mesh is legit? How do we know it's good enough? So that's what I have this part for. So if you open up your twist part, and I actually already have the study partially done for you. So if you go into this tab down here at the bottom, study 1, it's already got material applied as alloy steel, which is just whatever, some material, doesn't matter what. I have the bottom fixed, so the bottom face here is fixed. And I want to apply a load now. I'm going to do it at the top here. It's called twist, and that's for a reason. So I'll right click on loads, and I will do a torque. And I'm going to do it on this face at the top. So I'll select that face. And then it needs to know a torque about some axis, and that's what I've created this axis for in the middle. So you can select the axis there. And for the amount, newtons per meter, I'm going to go with 1,000. All right, and then that looks good. You can see how now which way it's rotating there. So we'll green check that. And for mesh, I'll just start with a coarse mesh at first. Let's see what we got here. So we'll slide all the way to coarse and green check that one. All right, so you can see how coarse that mesh is up to start with. And we'll zoom all there. All right, so let's go ahead and run this and see what we get. All right, so I want to focus in on the displacement stress. Or sorry, displacement. Displacement Distance, not stress. You can see here it's 8.8 millimeters overall, and then we can kind of see what's happening there. It's a little bit exaggerated here, so let's go to edit definition, and we'll change this to be a true scale. So what's the actual deflection look like? So again, we can see a decent amount of deflections happening there, and it's 8.82 millimeters. So remember the 8.82. So this is the part of the verification. When we verify our mesh, we want to make sure that it's sufficient that if we change it, if we get more, if we get a finer mesh, we don't see our results change. That's the key aspect to verifying our mesh. So we're just going to go back into mesh, and we're going to create mesh. Okay, and I'm going to select or enable mesh parameters. And you can see it's 0.01 is the distance here. So this is the global size, as I hover over this, the global size of all the elements. Now we're going to make this a little bit more fine. We're going to go to about half that size, and 0.5, so 0.005, so 5 millimeters is our distance there. All right. So we'll go ahead and green check that one, let it mesh up, and then we'll run it again and look at our results. All right, so going back into our displacement, there we go. So it's still true form, and you can see, oh, so it was 8.82, I think, right? So it's already changed to 9.078. So that's a decent change. So let's see what happens now if we decrease the mesh further. And we'll go down to 0.0033. Let's see what we get there. So we'll go ahead and green check on that one. All right. And what I'm doing is, if you look across the thickness here on the side, I'm basically doing it so that in the first case we had essentially one element across. With 0.5 millimeters, with 5 millimeters, we would have had only two elements. Now at 3.33 millimeters, we can get three elements across. And so that's what I'm attempting to do here. Is I'm changing that value based on how many elements I can get across that space if I reduce it the appropriate amount. So let's see what we get now for our displacement. And we're 9.097. I think it was 8 when the last one. This one's now to 9. So this is, better. You see it's not changing nearly as much as it did from the really coarse mesh to the 0.005 meters. Now let's do this one more time, see what we get here. So we're going to go and create mesh. And we'll go from 0.0033 to 0.0025 meters. So if we have 4 elements across the thickness there, so you can see the 4 elements across the thickness, and now we'll run it. And 9.074. So change a little bit again. Again, depending on what kind of accuracy you're looking for, you could go with the previous one. But ultimately, you want to keep reducing from 0.01 to 0.005, 0.003, 0.0025. You keep reducing until when you reduce it one more time, it doesn't change much. Then you can go back to the coarser mesh between those two, and that's the one you can use going forward, knowing that it doesn't change much if you make the grid any finer. So that's a great way to verify your mesh, confirm that it's sufficiently, the elements are sufficient to demonstrate you're capturing all that's happening in what's in the case. All right, so let's go back here. So verify. Before I get into that, I wanted to show you how to do this in Ansys real quick. I've already brought it into Ansys, the same twist geometry, and show you how we set this up. I'm not going to run it just for time's sake. But we're just connecting the geometry, open up model. I'm not too concerned about the material. Just go with the structural steel. That's the default there. All right, so it's in geometry. Again, we'll just check it though. We got structural steel So if we come in here to the mesh, we can just do the basic sizing. You can see we have the coarse mesh as default there, and we can update. So yeah, one element across right there. So if we click on mesh, hopefully you remember this from before, we can go to mesh control and sizing. And geometry, we want to select the whole body. So we'll come here for body select and apply that. And for element size, we'll go 0.005. It's in meters. So if we update that, we should have 2 elements across the thickness here. Yep, there we go. All right, so you can run this and follow the same process as we did in the SolidWorks case. All right, so that's the mesh verification piece I want to talk about. The next is finding min and max. So this is relatively simple. In both cases, you just need to find out where it's at. For Ansys, it shows up. Let's run this here now. Oh, that's regular. Apply my boundary conditions here. So we got insert the fixed support here at the bottom. Apply there. And at the top, we'll do a moment. Apply that magnitude of 1,000, and make sure the direction is what we want. Yep. Anything else? I think we're good. I need to say what plot. We want just deformation. So if we do total deformation, evaluate all results. Now we can see the twist there. And to do min and max is this button right here. So here's max. It'll show you the max point. Right? And the min will show you the min point down there. All right, so nice and easy how to do that. It actually shows over here what the values are for those as well. All right, so that's it in Ansys. So for SolidWorks, min and max isn't quite as available as a nice little button like it is in Ansys, but still relatively easy. So we just right click on our displacement, go into edit definition, and oops. Try that again here. Chart options, there we go. So show min annotation, show max annotation, which shows the min and max points and the actual values as well. All right, so that's under, again, chart options. So I right click on displacement or stress or strain as well, and go under chart options to access min and max. All right, so hopefully that was straightforward there. The next one is contacts. So in SolidWorks, trying to understand what contacts mean and how they work with each other is sometimes a little bit confusing. But they define how parts in an assembly interact when they come together. So bonded parts are fixed to each other at the interface. So here we have 2 plates, and if these plates get deflected downward, they will stay in contact right there the whole time. So there's actually no deflection happening in these pieces right here where they're bonded. No penetration. Parts slide on top of each other, can separate, but cannot penetrate each other. So these two can slide, push on each other, but they will actually, the pink piece will not go into the green piece like they can down here, where it's completely free, no interactions between the parts. They will pass right through each other. All right. So those are the 3 different kinds, and we'll look at those. Actually, let's look at it real quick here. So come in here, and we'll look under connections. Well, we actually need to do that real quick. So this is just a single part. We can't do this in an assembly. We can only do it in assembly. So let me open up an assembly. And we'll make assembly just of the twist parts. So I'll bring one in here. And then I will bring in insert component with just another twist part. And just kind of click it there. I want to get it in the right spot here. So let me mate it up here. So we'll do that surface in there. And other direction, good. And we'll do this surface and this surface. And then we'll do, we still need this surface here, and this one here. There we go. So it's right in the right spot there. All right, so let's see now if we would take this into a simulation. And we're just going to do a static simulation. So here's our contact. So there's our parts, our two twists, and then we have component contact. So this one, see, global contact is bonded. So let's edit definition and see what options we got. No penetration, bonded, and allow penetration. That's that free option. All right. So that's the kind of the three options that you would see. All right. So contact hierarchy. So how do these contacts apply to each other? Well, first of all, there's a global contact to any surfaces that are touching. So that's the one, if I go back here, that's the one that we already had here. So it's global contact identified as global. Anything that's touching is bonded. It doesn't matter if I declared it or not. If it's touching, it's bonded. So that's why when I get this, I can check or uncheck here. So the whole assembly, any place in the assembly is going to be bonded as it's selected here right now. The next one, or the one that would override the global contact, would be anytime someone declares a component contact on surfaces that are touching. So component contact is what this one's actually under. It's under a component contact, but it's also considered global. So we can get that through here. A component contact, I just right-click on connections. Component contact set is what we're talking about next. All right, so overrides the global contact to parts with component contact on surfaces that are touching. Solidworks overrides 1 and 2, so if it's a global contact or if it's a component contact, it will override it with any individually defined contact sets between specific faces. So contact sets are between this face and this face. Very, very specific call out for contact requirements. And so a little bit more information with that would be individual contact sets, probably should be R here, are the only way to apply contact to surfaces that are not touching. So usually we're doing contact declarations when things are actually touching each other. If they're not touching each other, contact sets is the only way that we can apply that contact restriction between things. Simulation, SolidWorks simulation, takes no notice of SolidWorks mates, only whether surfaces are touching or not. Right, so going back here to SolidWorks, I mated these two twists together right here. If I delete this, right, and there are no connections here, these two are not connected. Right? They are not, because of the mates I define in the SolidWorks, the part modeling assembly side, it doesn't actually mean in the simulation side that they're connected. So make sure you're aware of that. You still have to connect. And that's why the global contacts is usually just the default. If things are globally bonded to each other, you don't have to worry about declaring it because it's the global declaration takes care of all things touching. Next one, use interference detection with treat coincident as interference to find touching surfaces. So if you want to find things that are touching, to make sure you declare the right component contact declaration or contact set, you can use that. So let's look at what that is. So you can either go here under evaluate or under tools, the tools menu here, but what you're looking for is interference detection. So we're going to click on that, and so it's got the whole assembly here, and what we want to do is we want to treat coincidence as interference. All right, so if these two are coincident with each other, we want to treat that as interference so we can see where they're at. So go ahead and calculate, and let's see the other things down here too. The other one is make interfering parts transparent so we can see what's going on. So we'll click calculate, makes a little noise there, and you see really bright red, right, where this interference is happening. It's not actually interference because we said treat coincidence as interference. Let's actually take that off and we'll see that there's nothing. Right. So there's no interferences, but then if we just say, hey, we want to treat where the coincident, there is interference right there. All right, so that would tell us where we want to make sure we have some contact sets applied. We can also use automatic generation of contact sets to speed up contact definition. So this piece is when we're defining specifically contact sets of the two options here. So let me go in here. So we specifically defining contact sets. We can go in here and do automatically find contact sets. and we'll say touching faces, and it just has to, you need to tell it which components you want to look at. So we'll look at this one and this one, and we'll say, hey, find contact sets, and it finds it. Right? So there can be contacts between those two, and we can say, hey, what kind do we want? Bonded, no penetration, allow penetration. All right, and some other things we could define here. So I'm going to leave that, close that, and leave that as it is. All right, so that was it on the contact piece. Now I want to show where, how do you handle issues in your design and figure out what you actually need to apply the contact sets to. So let's go, let's do something a little bit more common. So I'm going to right click on connections, and I'm going to add back in that global contact that we normally would see when we come in. Normally it's bonded. That's the default, is a component contact, global contact that's bonded. I'm going to change it to no penetration, because a lot of cases you don't want these two parts bond to each other, but you do want them to not penetrate through it. You want it to slide on the surface or move around a little bit as it deflects. So I'm going to go with that. And we're going to set this model up here, so no penetration there. Fixtures, so we'll do a fixed geometry. I'm going to do it on the bottom of this guy here. And we'll apply that. And I'm also doing a load here. Let's just do a pressure on this surface. We'll do 500 Newton meters squared. So we'll confirm that. All right. So obviously, if this is not bonded to here, then we should see this slide away. So let's see what happens if we, we'll just go with the default mesh here. Well, let me see here. Maybe I'll just call this mesh. From before we said 0.033 is what we expect when we were twisting it. But anyways, we'll green check that. All right, so it looks good. So let's go ahead and run it now. Simulation and run. Oh, material, I didn't find the materials. Okay, so for twist 1 and twist 2, we'll just get the alloy steel again. Apply that to those. Now we should be able to run this. Looks like it's getting bogged down right here. So on purpose, I'm going to let this run the whole time so you can see what's going on here. So it says the iterative solver stopped. The solver has numerical difficulties. The model may not have adequate fixtures. No results saved. So it doesn't give you a whole lot of information. It took a little while for it to fail here. All right. So the thing I'm going to show you next, the strategies that are on the handout and what I'm showing you next, are to help this thing fail and fail quickly, or work and work quickly. But it doesn't give you results that you should use in the end. And I'll explain what that means as we go here. So the first thing I want you to do is to go up here to the study, right-click on it, and go to Properties. And I want to go down here to use soft springs to stabilize model. We talked about this before. I think this happened in Ansys. Turn it on somewhat ready. But what this does is it connects soft springs to every single node in our model when it runs the simulation. So these soft springs allow things to move, but not move too much in a way, so that basically if they're flying away, it'll still solve it, but it won't be the right results, but at least it gives you something that hey, here's your issue. You can see what's moving and what's taken off. So we'll click OK there. So use soft springs to stabilize the model. And the other thing we do is go over here to Mesh. Right-click on Mesh, Create Mesh. And the big thing is come down here, Advanced, and you want to use Draft Quality Mesh. The whole reason for Draft Quality Mesh is, again, we want this thing to fail. We want it to fail quickly. So the whole draft quality is to be, just do what needs to be done to get this thing to solve or fail quickly. All right, so that's what we want to see happen here. So we'll see our mesh here, but we already gave it some parameters. on the mesh side. So I'm going to see if we come back in here. If we take the mesh parameters off here, still got the draft. No, so it's still showing up there. But it will help in the process of speeding things up here. All right, so let's go ahead and run this. See how long this takes to run. I think it was about 43 seconds last time. All right, so excessive displacements were calculated in this model. So that's telling you something is really moving a lot. We'll just say no, solve it with small displacement. And whoa, it disappeared. All right, so let's look at our displacement plot. So our displacement is 5.6 times 10 to the 4th millimeters. So something's taken off here. These pieces are not a meter. They're very, very relatively small. So that piece flew away. I don't know where it went. Let's bring that piece back there. All right, but one of the things you can do to see it is you can edit definition and go, instead of true scale, let's go with automatic, and you see what it's at, 0.0006. And well, there's the part, right? So the whole part's just taken off because there's nothing holding it where it should be. All right, so using those techniques, the soft springs and the draft mesh are two key things that if your models, I would, unless you're confident it's going to be working the first time with the setup you have, I would even run that even the first time just to make sure everything looks good. But yeah, it's probably good just to run with what you guess, your basic conditions, a good mesh, and then if it does fail, come back, use the soft springs, and use the draft mesh so things can fail quickly, and you can get some information about what's going on. Hopefully things are just flying away. You need to lock them in a little bit more with the fixtures. All right, so that's what I have in this presentation. If you have any questions, put them in the comments below, and I hope to see you next time.